Hello, everyone, and welcome to our webinar today. Today, we will be talking about implementing microgrid solutions with Fronius inverters. And to do this with me is my colleague, Cyprian Okolo, who is a technical sales advisor for the Western African region. He's based in Lagos, Nigeria. And myself, David Mwangi, the technical sales advisor for the Eastern African region. And I'm based in Nairobi, Kenya. So our agenda for today, we will cover a few topics. So we will start off with the description of Fronius Offgrid and Backup solutions. And we will try to answer the question, why microgrid and backup solution? After that, then we will go into the Fronius AC coupling solution. We will talk about the basics of this solution, as well as the design and commissioning, what it requires. After that, my colleague Cyprian will take over and cover the PV-Genset solution, and he will also try to answer the question, why PV-Genset? And then finally, we will give you some useful information at the end of the webinar. So before we get started, please feel free to ask questions during the webinar. So you can type your chats in the questions area, and we will do our best as we go along to answer all the questions. Additionally, if you have some feedback that you'd like to give us on your opinion regarding the quality of the topics that are being covered, please, we also welcome you to do that. And you can also give us feedback through email or also via this webinar dashboard. So let's get started and look at the Fronius Offgrid and Backup solutions. So a microgrid and backup solution is really a solution that is engineered to give you grid independence or grid independent power supply. In addition to that, so when you bring a PV genset into the mix, we are looking at a solution that would allow optimal interaction between the PV system or the solar system and the diesel generator, all generators, if they are a number of generators in that setup. So when it comes to the backup and microgrid solution, we have a way of looking at it from Fronius in terms of how we define it. And in this case, we are talking about a setup that includes the Fronius string inverters, and then in combination with an inverter charger, then we would have a battery storage, and then the load that is supported by this setup. So the question then would be, why design a microgrid or a backup solution based on a Fronius kind of AC coupled principle? So first of all, this gives you independence from an unstable or non-existing grid. So it also provides an avenue for you to supply silent power for off-grid applications. And it is also a way to offer 24 hours of sun at its final destination, because you have the possibility now to generate during the day and store power in the battery system for use when the sun is not shining. In addition to this, then you are able to reduce significantly your carbon footprint. So therefore, the kind of customer segments that are suitable for this kind of solution would be the entire spectrum, really. And we are talking about small businesses. We are also talking about ecotourism. We are talking about homeowners, as well as village or rural electrification. So this solution then, we would have to make it in a way that it's capable, backup capable and scalable in terms of the required inverter chargers that are forming the grid. We would have also to ensure that there is an autonomous control mechanism. And in this case, for a Fronius grid-tied AC coupled system, we are talking about a frequency droop kind of principle that assures the proper functionality of this system overall. In addition to that, this would allow you to then maximize your solar share by converting energy more efficiently during peak demand periods. And in this case, we are talking about, for an AC coupled system, we would like to see the peak consumption being during the day when the PV inverters, or the Fronius inverters in this case, are able to convert energy very efficiently. So you can also then, as I mentioned, save the excess energy for off-peak consumption. And then, of course, this allows you to have maximum independence from fossil fuels in the case that you would have to use diesel generators as an example. So for this kind of a solution, in an AC coupled setup involving Fronius and Victron inverter chargers, the maximum AC power per cluster would be about 180 kilowatt. And then if more power is then required, you would have to combine several clusters. So in this case, then you can build systems that are even above a megawatt in AC power delivery. So let's now get into the principle of AC coupling, and we try to understand what this kind of a system or how this kind of a system looks like. So the typical setup for, let's say, off-grid applications would involve a DC coupled system. And in this case, we are talking about the direct connection of a PV generator to a storage system. As you can see here, we have the PV array, we have the MPPT charger, we have the battery storage, and then we have the inverter charger, and we have eventually the load that is being supplied by this system. When we talk about an AC coupled solution, we are then talking about the connection of PV power directly to the loads through the PV inverter, and then the possibility that any excess amount of energy that is not being consumed directly is then supplied to the batteries. So in this case, the inverter charger is able to operate in a sort of reverse direction because the Fronius inverter will be connected to the AC output. So in this case, the inverter charger is able to work in a reverse direction for charging the batteries. So you could also have a backup generator, as we can see here, number 5, or a grid for which then you would like to support with backup power, or if the grid is not very stable, then you form your own microgrid solution for this kind of setup or premises. To maximize on the benefits of those two configurations, both the DC and the AC coupling, we highly recommend that you have the possibility to combine these two. And therefore, we have the direct connection of the PV to storage and direct supply of the load. So in this case, you would have a portion of your PV array that is DC coupled to the battery system. And the biggest portion then also is connected to the PV inverter that then is able to supply directly to the loads during the day. So the choice then, whether you are doing AC or DC coupling, but like we have said, you can do a combination of both. But here is just to differentiate what each of these means. So when you have an AC coupled setup, it's ideal when the majority of the energy consumption is happening during the day. So therefore, you have a very high efficiency of energy or power conversion from DC to AC, which can be up to above 98% for Fronius inverters. The downside of this setup would be for the battery charging. So you can see we have slightly or low efficiency in this case. So if you compare this to a DC coupled system, you would have a lot higher efficiency for battery charging at above 98%. But with the DC coupled system, then you have less efficiency for direct supply of the connected AC load. So, and therefore this combination of the AC and DC coupling ensures that you are able to get the benefits of each of the configurations. So during the day, the batteries can recharge at a very high efficiency, but on the other side, because of the AC coupling, you are able to deliver your solar energy to the loads also at a very, very high efficiency. And this is really the biggest benefit you get out of doing a Fronius AC coupled installation. So let's now look at the frequency drop. So there requires to be optimal interaction between the Fronius inverter as well as the battery inverter, in this case, the Victron inverter charger. And therefore, we look at a situation whereby the PV array is generating sufficient amount of power, and all this power is then converted by the Fronius inverter. Some of it goes to the loads, and in this case, a lot of it is going through the Victron inverter for recharging the batteries. In the case that you do not have sufficient production by the PV array, so you can see here there is a minimal or minimized production, then the batteries through the Victron inverter should be able to cover the gap that is not being delivered by the PV side in this case. In addition to that, we also need to understand and make sure that when the battery is fully charged, the Victron inverter is able to react in a manner that allows or triggers the Fronius inverter to either increase or reduce the power output or the power production. So in this case, we can see that still we have very high production from the PV side. So a lot of this is being converted by the Fronius inverter, some of it going to the loads, but in this case, we have the battery at near state full of charge. So what needs to happen is that there needs to be some form of communication from the battery inverter to the Fronius inverter to tell the Fronius inverter that although we have very high production by the solar panels, we only need a certain amount of power in the network. And therefore, this is what we are referring to as the frequency drop communication between the Fronius and the Victron inverter. And therefore, there is an automatic power reduction when the battery is fully charged. And this is frequency dependent, as we have mentioned. And this happens by the Victron inverter increasing the output frequency. So with this increased AC frequency, the Fronius inverter then reduces the feed-in power into the network. So we can see this illustration through these two graphs. So we have to the left, the state of charge of the battery versus the operating frequency, as well as the maximum power production by the Fronius inverter versus the operating frequency. So as you can see, as the state of the battery approaches 90% or reaches 90%, the battery inverter in this case reacts by increasing the frequency, and it will start from 50 hertz all the way to 53 hertz. And this is up to when the battery then is fully charged at around 53 hertz. The response then by the Fronius inverter would be at 90% SOC when the frequency starts going towards 51 hertz. Then there is a power reduction by the Fronius inverter until around 53.5 hertz when the production is almost zero in this case. So this power reduction is also dependent on the connected load. So you could have a fully charged battery, but the load consumption during the day is quite high. And therefore, the Victron inverter is also able to balance the kind of operating frequency that is required so that most of what is produced by the Fronius inverter is supplied directly to the loads. So this is then what we refer to as the optimal interaction between the Fronius and the Victron inverter by frequency drop. So let's now talk about the configuration of an AC coupled setup. So for off-grid applications where microgrid solutions through AC coupling would be quite beneficial, but in other setups also, like we said, in a grid setup where the grid is not stable or where you want to give backup for the grid, You could use quite a number of battery inverters. So we have here the various inverters that can be used. But as mentioned, we have had a lot of systems done using the Fronius and Victron combination because the combination and the compatibility between the two inverters have been thoroughly tested. But if you do not have the Victron, you can also use the others that are listed here. So as far as the Fronius inverters are concerned, you can use both the single phase for residential systems as well as the three-phase inverters for commercial systems. And therefore, you're talking about inverters up to 27 kilowatts, but you can also use the Tauros, the Tauro 50 and 100 kilowatt also for AC coupling applications. So when it comes to the connection of the Fronius inverter to the Victron inverter, you have to decide whether you're going to connect it on the inside or the outside of the Victron inverter. So when you connect the Fronius inverter to the AC in of the Victron inverter, there is what we refer to as the factor rule 1. Then this is not taken into account when you are sizing the PV inverter. The downside to this kind of configuration of connection is that when the grid fails, then the Fronius inverter also stops working. The alternative then would be to have the connection of the Fronius inverter to the AC out of the Victron inverter. And in this case, then we have to consider the factor 1 rule. So this then has to be your guiding factor to be able to know how big of the PV inverter capacity should be used in that kind of setup. The benefit here is that if the grid fails, in the case that you have a grid connection, then the Fronius inverter is still able to operate because the battery inverter is able to sustain the operating voltage and frequency. So in this case, we have talked about already the interaction between the Fronius and the Victron inverter through frequency drop. And this is now what we refer to as the Fronius microgrid solution. So the other question you might ask yourself is, why Fronius plus Victron? So there has been a lot of collaboration efforts between Fronius and Victron for a very long time, and this has only resulted in strengthening of this partnership. We have various technical adaptations depending on the kind of systems that you want to do. So in the Fronius inverter, for example, you have the possibility to choose whether you're doing a setup for an MG50 or MG60 kind of microgrid, and this refers to the grid frequency that you're using. As far as the Victron side is concerned, you have also the possibility for implementation on the color control GX for the entire system scope. And you have the technical support commitment from both Victron and Fronius. And this is just an example that is put here with this link. So if you click on this link, you are going to go to a very detailed document that would allow you to design successfully and install and commission Fronius Victron microgrid solution. So when it comes to the connection, we have already talked about the possibility to connect either from the inside of the battery inverter or the AC out of the battery inverter. So as you can see, the Quattro as an example has 2 AC outs. So you can decide whether you want to support with your microgrid setup both AC out, but you can also single out what you would refer to as the critical loads, which then can be supported by the mix of the Fronius and the Victron inverters. As mentioned already, you have the perfect integration of the two solutions. So you have the color control GX that is used for local monitoring of the system. So when you have a Victron and a Fronius setup, you are able to see the operating parameters of the Fronius inverters within the color control GX. And you can see, for example, if it's a 3-phase inverter, what is the production of power per phase. You can also scroll within the pages provided, and you can see if you have any error codes within the Fronius inverters, you can see which Fronius inverter you are using. In this case, what was captured here was a Fronius Simo 8 kilowatt. This is a 3-phase inverter. And what is the status of this inverter? So in this case, it indicates that it is running. When it comes to monitoring, you can do monitoring from Fronius SolarWeb, and this would allow you to see PV production data only. But if you would also like to see consumption, you would have to install a Fronius smart meter. But for an AC coupled installation where the Fronius is connected to the AC out of the Victron inverter, a Fronius smart meter is not required. So in this case, if you then want to see the overall system, you can do this through the VRM. So this is the Victron monitoring platform. And here you are able to see the status of all the components that are used for the installation. So you can see the PV inverter, you can see the consumption as far as the AC loads are concerned. You can see the MPPT charger, if you have one, and also the state of charge of the batteries. So let's now talk about the design and commissioning. So when it comes to the design and commissioning of an AC coupled installation, we have talked about the rule 1-to-1. So in essence, this rule means that the peak power of the PV inverter must never exceed the power of the inverter charges. However, the PV array can and should be over-dimensioned according to the maximum allowable by the datasheet of the Fronius inverter. And then you have to select, when you're doing the commissioning, whether you're setting up an MG50 or MG60. So this allows more tolerant behavior concerning voltage and frequency operating limits. As mentioned already, with this kind of country setup or grid setup, you are able to have automatic power reduction when the battery is near fully charged by the Victron inverter. So it gives some frequency communication to the Fronius inverter to be able to respond accordingly. So in terms of planning and support, Fronius will support you with the design of the system. This includes the selection of the right inverters, the right string configuration, but the recommendations regarding the battery size will not be given by Fronius. This will be given by Victron. So if you go to the Victron website, so I've put a link here that you can also follow. So this tells you in terms of the battery capacity, depending on what is the total capacity of the PV array as well as the connected inverter chargers, what is the desirable kilowatt hour in terms of the battery capacity. And if you want to DC couple also some MPPTs, what are the design considerations or the sizing considerations for that as well. So when it comes to the commissioning process of the AC coupled installation, it's quite easy. Once you have done the installation and the wiring, you have to commission separately both the Victron and the Fronius inverters. So the Victron inverter, then you'd have to go through the various assistant wizards, and you would have to configure, for example, the PV assistant or the ESS, depending on which particular application you are doing. When it comes to the Fronius side of it, you have to, of course, supply AC power to the inverter. You have to select the country setup, and in this case, we talked about the MG50 or MG60. And this kind of microgrid setup can be done with both data manager-based inverters as well as pilot-based inverters. So all the snap inverters from 3 kilowatts up to 27 kilowatts from Fronius are fitted with the data manager, and the Tauro inverter and the Gen 24 Plus inverters are fitted instead with a pilot communication module. So both those two inverters can be used for microgrid setup. In terms of the data communication, if you're using now the data manager, this would allow you to communicate with the Fronius, the Victron Color Control GX. And in addition to that, it would allow you to connect internet to the Fronius inverter for you to be able to send the required data to Fronius SolarWeb for monitoring. So this is an illustration of a Fronius data manager card. So these are the various communication ports that are available. So we have here the Modbus TCP or LAN Ethernet, and this is the connection that then would allow you to connect to the color control GX, for example, through a router. So for you to establish then communication between the data manager and the GX device, you have to set up a local area network configuration. So what this means is that you have to set up a valid LAN IP in the Fronius data manager, and this is done using any of these methods. Method number one is DHCP addressing, or what we call dynamic IP. So if you have a DHCP server, you can connect the data manager with LAN, with a LAN cable to the same router as the Victron color control GX. In this case, then, the data manager is able to obtain the IP address automatically from the router. And the only thing here to ensure is that the IP switch of the data manager is in position B. The advantage of this approach would be ease of installation, and you are able to connect multiple Fronius inverters. If you have several Fronius inverters with the data manager card, and on top of that, it allows also the data manager card to acquire an internet access. The disadvantage is that it might take a bit long to search for the Fronius inverter, especially when you have a large subnet mask. The route number two for you to be able to connect the GX device to the Fronius data manager will be what we refer to as a link local addressing method. So this gives the data manager a predefined IP, and in this case, then a router is not required. So what needs to be done is to connect the data manager with a LAN cable to the LAN interface of the color control GX, and then make sure that the IP switch of the data manager is in position A, and then connect. You can also connect the Fronius and the color control GX on the same LAN network, either using a direct cable connection between the data manager and the color control GX, or if the installation between the two inverters is quite of a distance away, then you can use a network switch as well. So the Fronius will now have a predefined IP address, which is 169.254.0.180. The biggest advantage here is that you have low risk of communication failing, so no router is required. But the disadvantage is that the Fronius inverter does not have an internet access. And in addition to that, only one master Fronius inverter can be used when you're going through the link local addressing method. Alternative number three would be to connect the Fronius inverter or data manager through manual addressing method. And this is what we refer to as static IP assignment. So when you have a DHCP server, but you want to connect or to give the data manager a predefined IP address, all you have to do is to make sure that the IP switch of the data manager is in position B. Ensure that the subnet mask is the same as that of the color control GX, and then set a unique IP address, just like we know how to set IP addresses, and then set a gateway and then at the DNS for internet connectivity. So the advantage here is that it allows the Fronius inverter to have access to the internet, and the color control GX can search for the data manager very quickly. And the only disadvantage here would be that it's a bit more complicated to set up. So let's now look at export limitation. So for an AC coupled system, if you have the Fronius inverter connected to the Victron AC out, then you have to use the ESS system, and then you have to go to the Modbus settings of the data manager. So there is a procedure how you activate the Wi-Fi, the web user interface of the data manager. And once you are there, you go to settings, then Modbus, and at the Modbus, you're going to enter exactly what is shown here. So data export via Modbus, you select TCP, and then Modbus port is 502, string control address offset is 101, and then Sunspec type model is integer plus SF, and you have to also tick that you have to control the inverter via Modbus. When it comes to the control priorities, make sure that also Modbus has been given the highest control priority. So this, once you are done with this, then click on the Save button. For inverters that are connected to the AC in, then you have to use the Fronius smart meter and ensure that you activate the dynamic power reduction within the web user interface of the data manager. So, and you enter 0 as your preferred percentage of how much power should be going to the grid. So as a summary, you can use all the Fronius inverters for setting up a microgrid solution. We have talked about the special features with the country setup, frequency-dependent power reduction, and extended voltage and frequency limits. And in terms of compatibility, we have, as listed here, quite a number of inverters, but Victron, Quattro, and the Multiplus are really what have a lot of systems ongoing with the Fronius inverters. So long-term partnership with the Fronius and the Victron combo, we have technical adaptations, technical support commitment, as well as global trainings and education. So regardless of where you are and you want to set up a system using the combination of Fronius and Victron, you can be assured that you're going to require to receive the required support for a successful system setup. We have very many references, so I don't want to take too much time going through the references. So even in the Fronius website, we have a lot of references that you can go through. This is one of the examples, 82 kilowatt peak system in Spain. It is using 3 Fronius Simo 20 inverters with 6 Victron Quattros. And it also has 4 blue Victron chargers, 150/85. And in addition to the battery storage, it also incorporates a diesel generator. So in this case, 60 kVA. And we have done this thousands of times. So if you want to set up a Fronius Victron combo, you can be assured that, we already have thousands of systems already in place. It doesn't matter whether it's a small system or several hundred kilowatt systems. This can all be done with this combination. So, and at this point, I want to hand over to my colleague, Cyprian, who will take over and do the next bit of the presentation. So, Cyprian.
Yeah, thanks a lot, David, for a wonderful presentation. I want to believe that you can hear me clearly and can see my screen. Yeah, so next up, we decided that to spice up this presentation with a brief question and answer session, which will be all inclusive, meaning that we would want the participants or the attendees of this webinar to actively participate. So to start off, we're going to have the first question. So we're going to post this question, and it would require all attendees to log in and participate, just to spice up the session, like we mentioned, and of course measure your appreciation of the content of the webinar, per se, because we're going to be asking a question related to what David has presented in his own part of the presentation. So for you to participate, please kindly scan the QR code as can be seen, or alternatively, you can log into www.mentimeter.com or menti.com, and then you will be prompted to insert the code. It's nice to see that we have attendees already in the platform. So if you log in using the website www.menti.com, it will require a code. Please type in this code 1903848. You will be ushered into the platform. So I will wait for a couple of seconds more. I would really want as much attendees to participate in this as much as possible. Yeah. So once we've gathered enough attendees, I would just go ahead and with the question, and then we would prompt us to answer the question. Then after the questions have been attempted by the attendees, we will now reveal the answer and then continue. Great, I can see a number of attendees hitting the like button, meaning that they appreciate this innovation per se, to have something like this. So that's really nice and encouraging. Yeah, so we have 12 players ready. So yeah, I think we can go ahead. And well, it depends. If this turns out to be a successful practice, who knows? We might actually include a price tag during the participation. Well, let's just see how this goes eventually. So it's saying here that we have 13 players ready, probably 15 from the record here. So I will go ahead and ask the question. Good. So keep logging in. Of course, you have the QR code there. So the question is, what is the maximum system size cluster that is possible for a Fronius AC coupled setup? That is a Fronius Victron AC coupled installation. So what is the maximum system size per cluster that can be installed? Yeah. I believe my colleague David mentioned this previously during his presentation. So we have a 60 seconds window to answer this question. And the options are there already. It should appear on your screen on the respective devices you're using, probably on your phone. So all you need to do is to select which is correct. Is it 30 kilowatts, 90 kilowatts, 180 kilowatts, or 270? And we have about 5 seconds before it times out. Great. So of the options we posted, 12 went for 180 kilowatts, 2 went for 90, and then 1 went for 270. Of course, 1 also went for 30 kilowatts. Well, the majority that went for 180 kilowatts is correct. So that turns out to be the correct answer. Yeah, so just like David mentioned and during his presentation, you can have a maximum Victron Fronius Victron AC coupled system per cluster capacity of 180 kilowatts. Thanks a lot for participating. We shall now continue with my part of the presentation, which of course has to do with the PV-Genset solution. So before we continue, I'll just quickly want to correct an impression or an assertion that has been going on for some time. It might come to some of us as a surprise, but there are some, in this case, sometimes company executives or CEOs that assume that so long as the genset is operating or is running, then the rate of consumption of fuel is constant, no matter what the load consumption is. So that's absolutely wrong. We want to correct that assertion, and by, of course, telling us here that the rate of fuel consumption is equal to the load applied. Yeah, so once we have that in place, we can now continue, because at the end of the day, it means that the more the load, the more fuel consumption. So what we are coming in with this solution, as in the PV-Genset solution, is through this solution, we will be able to ensure a reduction of fuel consumption even while the genset is on, because once the fuel consumption is reduced, then of course you have the possibility of saving a lot of money to start with, and of course ensuring a longer lifespan of the genset. Good. So how can this be achieved? We shall go ahead and answer this in the subsequent slides. But first, why? While we're doing that, we need to address or to specify which customer target or target market we want to address this situation with. So first off, we are basically looking at big installation, big factory installations, tourism sector. Most especially, we have mining sector. In most cases, mining sites that are located in very remote areas. Most mining sites are actually located in remote areas that are oftentimes, disconnected or don't have access to the grid. And then, of course, large-scale food processing companies. So these are our target markets. One thing that these target markets have in common is that in most cases they have gensets, big gensets that are running almost perpetually. So why PV-Genset? Just as mentioned earlier, we intend to save money, then of course by reducing the rate of fuel consumption. This of course ensures the stability of the entire PV system, and then because of the way how retrofittable this solution is, it makes it very, very easy for integration even in an existing genset system. This, of course, ensures saving of money, of course, through lower energy cost, and of course, saving on fuel expenses. This in turn also leads to rapid amortization, and then importantly also, the decoupling from dependency on fossil fuel, and then this will in turn lead to a reduction in carbon footprint. So how is this achieved? So we're going to look at the components of this solution, just using that as a starting point. So having a quick look at the components responsible or that could be used to provide this solution, we have the Fronius inverter, then we have the diesel genset. This could be either single genset or multiple genset, but in each case, there are specific solutions to them. And then in the middle of it, we have the controlling mechanism, which I preferably call the brain of the system, because this is what aggregates between what is demanded from the genset and then supplies as much PV to complement the demand on the genset. And then, of course, we have the load, which is, of course, the target of these various sources of energy. So going forward, now let's have an overview of the entire system by defining each of these components. So this is like a single line diagram of the PV-Genset solution. So to start off, we have the Fronius inverter, which converts the DC to AC, of course, and then supplies it to the AC line, the common AC bus bar. Then we have the PV system controller, like I earlier defined, as the heart or the brain of the system, which of course measures the power flow, the entire system power flow, and then determines when to throttle up or throttle down the PV supply into the system. Same effect also is handed to the genset also, determine when to ramp down with the complement of the PV injection into the system. Yeah, the genset, of course, is the primary source of energy in this system. Like I said, we target setups that have gensets that are almost perpetually running. So this genset tends to be the primary source of energy for this system. And then we now look at the loads that are being supplied with optimal mix of the earlier said sources of power. And then most importantly, there is a device or component that plays a very, very critical role. Those are the current transformers or the current sensors. So they are attached to the PV system, and then they are able to read how much current is being drawn from the load. So this now enables the system controller to determine how much power should be drawn from any of these sources, basically. And then, of course, we have the grid, which in some cases for our target market might be limited or unavailable completely. Good. So having gone through the definition, let's now look at how we can actually implement this. It can come in different fashions. It can come in the low penetration angle or perspective. So with low PV penetration, it basically entails the injection of PV to complement the gensets. But then in this case, the PV injection is usually low. And in this case, it doesn't really require the implementation of a PV system controller. We're talking typically from 15 to 20% of PV injection relative to the capacity of the genset. So when you have such scenarios, a PV system controller is not absolutely necessary. So in a scenario where you have a high PV penetration, this is where we have enough or a high volume of PV installed in the system. In some cases, as you can see from this power curve, PV curve, in some cases you could have the PV just submounting or just above the load demand. So it is absolutely necessary for us to have a dynamic control of the PV, because if this doesn't happen, or if this is not applied, then we would have damage to the genset or the inverters installed, because you could have, or of course, there's a high possibility of the genset being turned into a motor, or basically having a negative feedback. So these are scenarios that we need to, have control over. And then, yeah, so like we can see from this PV curve, this red line basically tells us basically represents the PV generation curve. And then this dark gray region, as you can see in this case, represents the impact of the PV on the system. Then this light gray represents the power drawn from the genset. So basically, the genset is relieved of its load by the percentage, or by the region, as you can see, that is colored by the dark gray region. Good. Now, continuing, we're now going to delve more into the PV-Genset controller, and then how its main task, and then how a system can basically be designed using the information that will be given to us subsequently. So basically, the main task of the PV system controller is to protect the diesel generator, like I mentioned earlier in the previous slide, because if it doesn't protect it, then there's a high possibility of having a negative feedback depending on the injection of PV in the system. So by so saying, it is now imperative that we do a proper load profiling before we can properly design a system. So starting off, it is necessary for us to know the peak load demand of any system that we intend to implement this solution in, and then of course have the minimum genset loading information. This information is always it always comes with the genset from the manufacturer, so it's can easily locate this on the genset nameplate. So once we're able to ascertain the minimum genset loading, then we can extrapolate the inverter capacity that would be installed, and then from the inverter capacity with its oversizing ratio, we can now determine how much PV can be installed, how much PV that can be installed in this particular system. So that's basically a rough way to design a PV genset system. Good. So yeah, that's basically how we roll. And I want to inform us of the types of PV genset solutions that are available. Yeah, so we have the PV Genset Advanced and then the PV Genset Professional. At this point, I would say that we've not forgotten about the PV-Genset Easy, which used to be the case with the Fronius PV-Genset system controller, but then this has actually been discontinued. But then, just to mention that we still provide maximum support for all systems that has it installed. Good. So going forward, for the PV-Genset Advanced and Professional Solution, they're both the same thing, just in the case of application that they differ a bit. So given the single line diagram, as you can see in this case, just like the slide I made mention or defined the entire solution with, it's basically entails the implementation or the integration of the system controller. It could be on an already existing system. So in that case, we call it the PV-Genset Advanced solution. So in this case, it just entails the integration or the retrofitting of a system controller into an already existing genset system. And then for the professional solution, this you could have a situation, or this entails a situation where apart from the system controller, you have multiple gensets that also have their respective controllers. So that, and in most cases, these controllers and the system controller are actually from the same manufacturer. So that they can easily talk to each other, communicate to each other in the same language, per se. So that's basically the main difference between the PV-Genset Advanced or the professional solution. So putting it in context, you could say that the PV-Genset Advanced could be applied for brownfield installation, while the professional could be easily applied for greenfield installations. And if you look closely, you can see that we have a battery backup system here. So this can easily be integrated in any of these solutions. So you have it coming in handy in scenarios where you have the battery banks stepping in occasions where the load or the consumption is very minimal, that wouldn't necessarily require the genset to run. So that comes in as a very, very wonderful addition to the entire solution. Good. So I'll just quickly give us a reference here. So we have this reference in Lebanon. This is an irrigation farm that implemented this PV-Genset solution in December of 2014. And I can happily tell you that this system has since attained complete amortization, much to the benefit of the owners of the system. Yes, so I have also included a link. So with this link, you're going to have access to this particular installation and then to other PV-Genset solutions. So please, once the presentation slides are shared with you, eventually after this webinar, you can of course click on this link and then it will take you to other solutions apart from this one that has been implemented using the Fronius PV-Genset solution. Good. Now, to put it in more detailed context, using that same system that was installed in Lebanon, the system actually cost 216,000 euros, which is quite a lot of money. The PV installed capacity was about 150 kilowatts peak, and then the localized cost of energy for this system was 0.15 kilowatts hour. And as at then, the diesel cost was going for 0.5 kilowatt hour. And then once installation was done, we had an annual PV plant yield of 200 kilowatt hour with an annual savings of 45,000 euros. So that was the initial annual savings. But then, of course, we know that diesel costs eventually increased, and then also the annual savings also increased, because with the increase in diesel costs, and of course with the reduction in the consumption of fuel, of course this will lead to an increase in the annual savings. Yeah, so we have put a bracket of between 4 to 8 years for achieving amortization. But for this particular system, amortization was actually achieved from the 5th year with an annual savings of 68,500, just about 70,000 euros per year, which comes in at a very, very wonderful achievement in that regard. So rounding up with recommendations, yes, like earlier said, please ensure that you have 30% minimum genset loading unless stated otherwise by the genset manufacturer. And then to complement this, ensure that the maximum AC inverter power does not exceed 70% or slightly lower than that. And then, of course, it is important for us to, for the client or for the installer to know the load profile of the system. This is, of course, to react to changing load requirements in the system as time goes on. So continuing with the recommendations, please ensure that you ramp up the DC to AC ratio as much as possible by taking advantage of the over-dimensioning feature of our inverters. Most of our inverters, or all of our inverters, can actually be over-dimensioned up to 150%. So once you ensure that it is possible to garner or harness as much PV power to inject into the system, please ensure that during the PV Genset Advanced or Professional, ensure that you have the right configuration of the controller. Same thing applies to the PV Genset Easy solution. Good. So going forward, it is important to note here that the reaction time of every PV genset system is of utmost importance, because in a case where the system is not able to react as fast as possible, then there could be trouble, especially on the genset side. So, which is why we have this real case scenario, a graph of the reaction time of our controller, of the plant controller, that is. So you have the consumption level in this case, as in load consumption, and then you have the genset output, which is at the moment, at this point, at the minimum genset loading. So what happens in this case is that we have the PV being injected. So if there is a sudden reduction in load, say a heavy machine was turned off, so it means that the load demand will drop also. So once this drops, it is absolutely important, very important, that the PV also reacts in the same manner. Otherwise, there will be an overload of PV, which will, of course, negatively affect the genset. So as we can see in this case, that is exactly what happens. As there was a sudden drop in the consumption, there was an equivalent drop in the PV injection into the system to ensure that the load is supplied with the optimal mix of PV and the minimum genset loading. So this continued, and then until there was another increase in loads, probably the machine that was turned off earlier was now turned back on, and then this, of course, is followed with a ramping up of the PV injection. Of course, this is relative or subjective to the PV or the radiation supply at this point in time. Good. So going forward, let's now give us a recommendation, power range recommendation. So a sweet spot for applying the PV Genset Advanced is usually put at between 100 kilowatts to 2 megawatts. Okay, you might want to go below or above that, but then we're looking at the economy of scale and then the cost of components. So the sweet spot would preferably, or it's recommended to fall in between 100 to 2 megawatts. Then for the professional PV genset solution, comprising of multiple genset system, sweet spot is recommended to be between 200 kilowatts and 5 megawatts. No harm going slightly below this, of course. Good. Fronius on its part also provides support when it comes to the PV-Genset design, solution design. So you can, of course, reach out to us using the checklist, which can be found on our homepage. So once you fill out the checklist, we can, of course, support you in terms of system planning, and then, of course, eventually patch you up with the respective third-party plant controller manufacturers, as you can see already listed on your screen. Good. So let's now follow up with the second and last Menti question for this webinar. So quickly log in, and I would also want the attendees to also do same. So please scan the QR code. Yes, this is beautiful. I can see many of you already logging in. We have 9, 10 already. So because of want of time, we might not have time to accommodate as much as would have initially wanted. So please see if we can log in the next 10 seconds, and then I would now launch the second question for this presentation. Good, we have 15 already. So the QR code will still be displayed even while I post the question. So please go ahead and log in as I post the question. So the next question is, how does the plant controller communicate with the Fronius inverters? So we have 4 options here, via Bluetooth, via PLC, that is power line carrier, we have via Modbus, or via Wi-Fi. So we also have a 60 seconds time limit to answer this question. That says, how does the plant controller communicate with the Fronius inverters? Is it through Bluetooth? Is it through power line communication or carrier? Is it through Modbus, or is it through Wi-Fi? Good, thanks a lot. It says that everyone has voted. So yes, we can now see the answer. Yeah, so it says here from our choices, from the attendees' choices, 1 person went for power line carrier, 18 went for Modbus. So which is correct in this case. So the medium for communication between the plant controller and the Fronius inverters through Modbus communication. Thank you very much for your participation. This is very much appreciated. So continuing with our presentation is, of course, as we can see, obviously is the answer to our second Mentimeter question, which is the communication interface. So communication interface between the controller, in this case, for this example, is the Illum hybrid fuel saver controller with the Fronius Tauro inverter. In this case, it can, of course, it is via Modbus. So Modbus, it could either be Modbus RTU or Modbus TCP. It is also possible to communicate via the API using the JSON protocol. And then, of course, you can, of course, implement internet connectivity via wireless LAN or network cable. So same thing is also applied for all Fronius snap inverters, but then it is important to ensure that we have at least 1 data manager in the cluster or in the SolarNet ring. So please ensure that the optimal number of snap inverters are connected per SolarNet ring. So for most third-party devices, it tends to recommend 6 snap inverters per SolarNet ring. Okay, so this is, of course, to ensure the fastest communication and reaction time for the PV-Genset setup. Good. So finally, let's have a look at the Fronius inverters that can be used to provide this solution. And of course, probably I've not given us a sneak peek from the previous slide. So of course, we can implement this using all our Fronius Snap inverter classes, both the Primo, Simo, and the Echo. We can also implement it using the Gen 24 inverters, and then of course the Fronius Taro inverters. Great. That brings us to the end of our presentation today, but then would want to leave us with brief information. Yeah, so this is basically about recordings. So all our recordings are actually available on our homepage, where you can have access to all operating and installation instructions. You can also log into our YouTube channel, where you can obtain or have access to all our how-to and installation videos. Then specifically, you can actually have access to all our webinars that have been published in our Sub-Saharan Africa playlist via this link. So with this link, you will be able to have access to all the webinars that we have published so far, including this one, which will be posted subsequently. Yeah, so for further information, in case you have inquiries based on some technical questions, training, sales, and after sales, please make sure do well to contact us via this contact details that have been stated here. And if you want to contact us directly, that is the TSAs, please go ahead and contact me, Cyprian Okolo, responsible for the Western Africa region, Byron Costa, who is responsible for the Southern Africa region, and then David Mwangi, who's with me in this webinar today, and is also responsible for the Eastern Africa region. Good. So with this, we have come to the end of today's webinar. We want to believe that we all enjoyed the content of this webinar and want to especially appreciate us, the attendees, for attending this webinar, and I hope you enjoyed the content. So until we come your way next time, do enjoy the rest of the day. So for me and David, this is saying thank you and goodbye.